right, so an introduction of transformations of functions. This is a review of section 2.4. So we're going to start with vertical shifts. So if c is greater than 0, basically the y equals f of x plus c shifts the graph upward c units. So here's an example where we have a y equals x squared plus 3. We can look at the parent function, which is y equals x squared, and it shifts upwards 3 units, making it y equals x squared plus 3. Now, an example of y equals f of x minus c, we're going to shift the graph downward c units. So an example here would be y equals x squared minus 3. Once again, we have our parent function of y equals x squared, and it goes down 3 units, making it y equals x squared minus 3. Now for horizontal shifts, we have y equals f of x minus c shifts the graph to the right c units. So we can see an example here of y equals x minus 4 squared. We can see the parent function or parent graph is y equals x squared, and then we shift 4 units to the right, giving us y equals x minus 4 squared. And then with y equals f of x plus c, shifts the graph to the left c units. So an example here is y equals x plus 4 squared. We can see our parent graph, y equals x squared, going to the left 4 units, hitting -4 actually, but our function is y equals x plus 4 squared. All right, so now talking about reflections, there will be an example of these, but I'm just going to talk about the general requirements and expectations of reflections. So for y equals negative f of x, it is the reflection of y equals f of x across the x-axis. For y equals f of negative x, it's the reflection across the y-axis. And then y equals negative 5 times negative x is the reflection across both axes. So it's same as a 180 rotation about the origin. Now for vertical stretching and shrinking, pretty much y equals cf of x. So we have 2 rules. So if c is greater than 1, the graph is stretched vertically by a factor of c. But if c is in between 0 and 1, the graph is shrunk vertically by a factor of c. So we can just understand that vertical stretch is going to be narrowing the graph, so our y values grow faster, whereas vertical shrinking is going to be widening the graph, so y values will grow slower. So we can see an example right here that we have our parent function y equals x squared, just a typical parabola. But then when we see a vertical stretch at y equals 3x squared, we can see that it starts getting narrower. And then at y equals 1 over 3x squared, that is a vertical shrink, so it starts getting wider. Now for horizontal stretching and shrinking. So y equals f of cx, we can see that if c is greater than 1, the graph is shrunk horizontally by a factor of 1 over c. And then if c is in between 0 and 1, the graph is stretched horizontally by a factor of 1 over c. So we can see here on this example right here that we have y equals f of 2x. So the graph is going to shrink horizontally by a factor of 1/2. It's going to be the opposite of 2, and it's going to be 1/2. So we can see here it's very shrinked, very tight of the zigzags. And then for this example, we have y equals f of 1/2 x. The graph is going to stretch horizontally by a factor of 2, so we can see that the zigzags are starting to widen. And then for our inverse functions, the graph of y equals f of -1 of x is the reflection of y equals f of x across the line y equals x. So we can see y equals f of x, for example, it hits the point 0, 1, and then we have our y equals x line, and then we will have a reflection being the inverse y equals f of -1 x, and it's at 1, 0. Now for problem 1, which is graphing transformations. So we have to consider the exponential function, which is f of x equals 2 to the x. We're going to sketch and describe the transformations for each of the following. So we have g of x equals 2 to the -x. We have h of x equals negative 2 to the x, and k of x equals negative 2 to the negative x. And we will explain how each graph is related to the parent graph y equals 2 to the x. So here we can see that our parent graph is at f of x equals 2 to the x, and we can see that it hits the point 0, 1. So to get the g of x graph, we need to reflect across the y-axis, which is going to give us g of x equals 2 to the negative x. Now, if we want to find h of x equals negative 2 to the x, we're going to reflect our parent graph over the x-axis, and that is where we get our h of x equals negative 2 to the x. And then with our k of x equals negative 2 to the negative x, we are going to reflect over the y-axis and then over the x-axis, giving us this right here. And they both hit the point negative 1, 0. Now for problem 2, we are going to be solving algebraically and graphically. So we're going to solve the equation both algebraically and by showing on a graph e to the 3 minus 2x equals 4. So we're going to find x, we're going to sketch the graphs of e to the 3 minus 2x equals 4, or I'm sorry, just y equals e to the 3 minus 2x, and y equals 4, and we're going to show the intersection point, and then we are going to explain how the algebraic and graphical solutions agree. So pretty much right here we have where we're solving e to the 3 minus 2x equals 4, we are going to take the inverse of e and we're going to put the natural logarithm. And so we put that there, and that leads us to bringing out the exponent outside. It's multiplied by the natural log times e. The natural log times e actually ends up canceling, so we're left with 3 minus 2x equals in 4. And so we subtract 3 on both sides, and then once we get that, we bring down the negative 2x and everything with it, and then we divide by negative 2 on both sides. We get natural log of 4 minus 3 divided by negative 2, and we can take that negative from the 2 and distribute it, leaving us with the flipped version, 3 minus natural log times 4, of 4 over 2. And then over here we can see our graph, where first off we had to make this simplified to this. So we basically just flip it to negative 2x plus 3, and we kind of just take out the negative 2, and we're left with e to the negative 2 times x minus 3 over 2. So basically here we have the horizontal shift of 1.5 units, which is 3 over 2. We have a horizontal shrink by 1/2, and we have a reflection over the y-axis because it is a decay. It's an exponential decay because we have a negative in the exponent next to x. And then we have to basically have a horizontal shrink because we have a coefficient next to the x. So then we have y equals 4, and they both intersect at the 0, 4 point. So basically the algebra gives the intersection at x equals 3 minus natural log of 4 over 2, and the graph shows the exponential curve crosses the line y equals 4 at the same spot. So both ways show the same point. All right, so problem 3 is inverse relationships. So we're going to let f of x equal e to the x plus 4 plus 1. We're going to find its inverse function, which is f of negative 1 of x. We're going to sketch both graphs on the same axes, including the line y equals x. We are going to explain why logarithmic functions are reflections of exponential functions across y equals x. So basically here we're going to find the inverse, and so we have the f of x equals e to the x plus 4 plus 1. We make that y because it's the same thing. Subtract 1 on both sides. We have y minus 1 equals e to the x plus 4. We take the natural log so we can get rid of this e, and then we end up with our exponent being taken out. We can cancel out the log and the e because they cancel out each other, they're inverses. And then we subtract 4 on both sides, and we're left with x equals natural log of y minus 1 minus 4. And we basically switch that to an x because it's the inverse. Now over here we can see on the graph that we have the y equals x line. We have an asymptote of y equals 1 for the e to the x plus 4 plus 1 because y equals 1. And then because we have this asymptote of y equals 1, the graph is shifted to pass through the point -4, 2. And then over here we have the inverse, and we have the point 2, -4, and the asymptote is x equals 1. And so over here, logarithms are the inverse of exponentials, so their graphs swap x and y. This reflection across the line y equals x shows that every point on the exponential has a mirror point on the logarithm. Lastly, problem 4, putting it all together. So we're going to consider the function f of x equals -3 times the natural log of x minus 2. So we're going to identify the domain, vertical asymptote, and intercepts. We're going to describe the transformations from the parent y equals natural log of x. We're going to sketch the graph and show how each transformation is applied, and we're going to explain how this function illustrates the horizontal shift, vertical stretch, reflection across the x-axis, and the inverse relationship to an exponential function. So we can see right here that from our f of x equals -3 times the natural log of x minus 2, that we have a domain of 2 to infinity, and then our vertical asymptote is at x equals 2 because when we do x minus 2 equals 0, we end up getting x equals 2 as our asymptote. And then we have our x-intercept is 3, 0. By solving, we set it equal to 0, and then we get x equals 3. Then we have, for our y-intercept, it's not defined because x equals 0 is not in the domain. Our reflection is across the x-axis due to the negative. So you can see here when we have a negative outside the parentheses, we have a reflection over the x. My bad, the x. And then the vertical stretch by a factor of 3 because our c is greater than 1. So it's a vertical stretch. And then for the last point right here, the inverse relationship to an exponential function, we have right here that this function shows the inverse of an exponential because if you solve for x, you get x equals 2 plus e to the negative y over 3. Logarithms undo exponentials, so the log and its exponential inverse are mirror images across y equals x.